Excellent. Thank you so much. So our featured speaker today is Roice Nelson, who's a software developer with Aerospace and has a passion for exploring mathematics through visualization. You might have encountered his mathematical Twitter bot, TilingBot, which generates and posts new tilings every day, I think, on Twitter or maybe X at this point. His article, Abstracting the Rubik's Cube, became part of 2019's Best Writing on Mathematics book, and he has so many other beautiful projects. I'm a p-adic geometer myself, and so his sort of collaboration with Edmund Harris, to illustrate the p-adic numbers is something I found super beautiful. Go to his website sometime; it's so fun. And one more thing, together with his wife Sarah, Roy started an endowment for mathematics outreach at UT Austin, which has helped with their Sunday morning math group for a few years now. So Royce told me that for him, to see something mathematical often means coding the ideas and rendering the image. And so I'm sure we'll see some examples of that today. Thanks for joining us, Royce.
Thank you. Can you hear me? Okay. Thanks so much. It's really cool. I love these online seminars, and I was telling Aaron when we were starting off that it's cool to participate and be on the other side of it. And thanks for the invite, Gabriel and Aaron, and thanks for the introduction. I didn't know what to talk about when Gabriel reached out, but I decided to go with this, what I'm going to call abstract regular illustration. And it's just adventures that I've had over the last 10 years, digging into a couple of groups. I thought about calling it projective special linear illustration because the PSL27 and PSL249 are the groups. The picture, the left is a picture of the first one, and the right is a picture of the second one, and we'll go through those. I try to put pictures on every slide, and I'm almost 100%, but not quite. So there's going to be lots of pictures to look at. This slide's mostly for me. It's the I'm legit enough to be here slide, but it's mostly for me. And I just wanted to use it as a moment to reinforce how this community has been great for me. I've really enjoyed working with a number of people over the years, and I hope for more of that in the future. The p-adics was one thing. I worked on honeycombs with Henry, Clifford Torsting with Scott Wortman, abstract polytopes with Non, minimal surfaces with someone who's not here, and more, and I hope for more of that. So also my cat Coco spends a lot of time with me, and she's here. This is cat pictures making it into my talk, and she's right here too. Hopefully she will be mostly cooperative. All right, so this is what the talk's about. The talk is about making this analogy work as good as possible. So we have the dodecahedron. On the left, we have the dodecahedron to the 120 cell. And on the right, we have the Klein quartic, which many of you will be familiar with. And so what's the analogy of those things, and how can we make them fit as much as possible? So for those who don't know, the Klein quartic is, instead of a shape with 12 pentagons, it's a shape with 24 heptagons. It is, I don't think people typically think of it as an abstract regular polytope, but it is, because what puts something over the line to that is the geometry doesn't fit together as nicely as things do, like for the dodecahedron. And I think this is interesting too, because the 120 cell is not considered an abstract regular polytope. It's just a regular polytope, but it is very abstract too, because it lives in a higher dimensional space that we don't live in. And so even though it's not normally considered that, it is. And the Klein quartic, I think, for similar but different reasons, doesn't usually fall into this category of abstract regular polytopes, but it is very abstract as well. And we'll dig into some of that. One of the themes of this talk is that the whole question of, if I were math god, how would I do it? And up at the top there, I'm showing all the orientation preserving groups for these objects. So it goes PSL25, then the 120 cell is an outlier here. It's a Coxeter group. The Klein quartic is PSL27, and the 350 cell is PSL249. So if I were math god, I think I would have made it PSL225, but it's not that. And we're just gonna have to live with that. And there's gonna be other cases of that, but in terms of making this analogy fit, that's kind of a theme of this talk as well. Okay, puzzles are gonna make an entrance here, and I did see, like, hi Luna. I posted this on the hypercubing group because this is my history with these objects. So we have a puzzle there made of the dodecahedron. It's like a Rubik's cube. I wrote this program called Magic 120 Cell, which was a 4D version of that just 15 years ago plus, and the hypercubing group was very excited about it, and people have solved this. And then later I wrote a puzzle that lets you play a Rubik's-like puzzle on the Klein Quartic. And so this is really the question in that domain. And so puzzles are gonna I tried to not make it too puzzle centric, but puzzles do make an appearance because it's part of my history with these questions. All right, when Gabriel first reached out, I was thinking about what I wanted to do here. I went and reread the On Proof and Progress in Mathematics by Thurston. And in that, I really recommend revisiting it. It was great to do it. In that, he asked the question, why do we do math? And he had this great quote at the top, which isn't answering that, but it said, mathematicians usually have fewer and poorer figures in their papers and books than in their heads. And but the important part for me is the next line, which is what we are doing is finding a way for people to understand and think about mathematics. And so I asked myself the same thing about mathematical illustration, and that really fit to me. Like, it's really, in the end, it's about us understanding both for ourselves and understanding and communicating with other people. I've found for me the act of illustrating is a huge way to make small steps in personal understanding. And for me, that's a lot of that's programming, but I think it's different for different people. And I also, in preparing for this talk, this was really fun to kind of get back into this project. I'd fallen away from it a little bit, and I made a bunch more recent jumps, which were really cool. And being able to share that with y'all too as well. So the act of sharing, the act of doing it yourself, and then the act of sharing with other people just allows us all to connect up. And so I thought this was cool. By the way, I'm gonna have a link at the end. I have all these slides. It's Google Slides, and there's a lot of links in the slides. So you'll be able to go revisit this and get a link to that paper and other links that I have in here. Okay, so let's talk about that picture I had on the first thing, which is a pretty ugly picture. And I went ahead and made this my ugliest slide too, because I figured it could go with the picture. So I'm in this hypercubing group, and we do all this 4D, zoom the puzzles around, look at them. And then I read somewhere that the Klein Quartic lives in 4D, and I didn't know what that meant. But I was like, oh, we know 4D, so let's make a Klein Quartic viewer to understand it. And so I'm going to go ahead and read this. This is from the email on that hypercubing thread. What I did was I calculated the coordinates. So the coordinates of this actually live in complex 3 space. Well, I'll just read this. Calculate the coordinates of the KQ vertices in C3 with the help of Klein's paper. And I have a link to that too. There are 168 of these, but the same point shows up 7 times along a projective ray. So we identify all of those to get the 24 centers of the heptagons, and that lives in complex projective space, CP2. To do that, we normalize all the points, and we see which get the same value. After normalizing them, what I found when I was coding this stuff is that even though they didn't live in C2, they still kind of lived in C3, even though I had the same value for all of them. So then I had projected all those vertices down to C2. And now we have a 4D thing and that we can interpret in R4 because we just have 4 coordinates. And so I was like, yeah, hallelujah, we can do that. The points were not bound to this 3 sphere, which it's really nice when they are. It makes drawing these kinds of pictures easier. And I did a typical visualization and had some controls. I resurrected them enough to make this picture, but I didn't resurrect them. I use an old technology called Silverlight, and it's been retired by Microsoft. I didn't resurrect it enough to zoom around, but this is kind of what the picture looked like, except you could zoom it around and 40. And I was really disappointed. It was, in a sense, it was a complete failure. Like the picture was not understanding inducing. But from the point of view of understanding and my personal growth in mathematics, it was a huge success because I didn't know anything about complex projective space. And when it lived in 4D, what I initially interpreted that at turned out to be very different than what it ultimately was. So this is an illustration win, even though the illustration is not a win. I have a few slides throughout that I just have with this title. What does mathematical illustration actually look like for me? I thought I would just share a little bit behind the curtain. This was 10 years ago. My wife, Sarah, she posted this and she said, not uncommon to find things like this lying around my house. And this is typical. And I even found while I was preparing for this talk, I still had all, scribbles over the paper. So that's a common thing for me. I have a few more to share a little bit later too as well. So I just have a few of these slides throughout the talk. Oops, way. Okay, so we'll jump onto puzzles just for a little bit here. And okay, good. They're working. I was worried my GIFs wouldn't work. So when I first posted this Klein-Kortic puzzle on the cubing group, they've solved it fast. People jump in, and one of the things that was very interesting is a bit in the beginning, and Thurston says this in a book about this object, is that if you start, unlike the dodecahedron, there's one opposite face on the dodecahedron. On the Klein-Kortic, there's two. So if you start solving the puzzle from top to bottom, as is common on a Rubik's Cube, what you'll find at the end, towards the end, is that you'll have two unsolved faces instead of three. And you can see them here. If you just look at sort of the x-axis, you can see my mouse going left and right here. You'll see those three. So there's kind of a bluish one on the left, the white one in the middle, and a greenish one on the right. And you can see the identified tiles twisting as part of that puzzle when you twist one and ones on the right. The white one is as well, but they're harder to see because it's closer to the edge. Those blue and green ones are, the centers of those are at the vertices of that 14 gone on that first picture of the Klein-Kortic, but this is showing that this whole cover of the 7-3 tiling. So anyway, the point I wanted to make here is that the interacting is even yet another level of interacting with illustration. I was thinking of Dana and Madonna's stuff that I've seen here recently with the tessellations and the hyperbolic crochet, and how much that can also get us past our own personal walls of understanding. And it's the same is true in this puzzle world. I went ahead and threw the equation, the original equation from Klein's paper up here, just as it illustrates it as well, but it's very different. These side by side is just, they seem like completely worlds apart, but they're the same thing. Another fun thing that happened, and I'm not going to spend a lot of time on this slide, but there's two opposite faces, but there's when you look at edges, there's actually three opposite ones. So there's four sets of edges that are kind of opposite to each other. And when you look at vertices, there's only one opposite vertex. And you can see this here when we tried to make checkerboard patterns, which is something you do on Rubik's Cubes. We try to do them with these puzzles too as well. You can see on the left here, this is an edge stabilized checkerboard. So there's four sets of edge pairs in here that checkerboard each other. And then over at the right is the vertex stabilized, and there's this vertex right here and this vertex right here are the two opposing ones. And so you're able to make Klein-Kortic checkerboard patterns in these puzzles for that. You can't actually do it with the face stabilized, and I have a link to, which is really interesting and connects to how checkerboards happen on the Rubik's Cube too as well, and I have a link to our online discussion about that there at the bottom. Okay, so this is really fun to share because this is new as of doing this talk. So what happened was in 2019 at the Illustrating Math thing at Brown, Arnaud Chertot said to me that the idea of using the systolic pants decomposition of the Klein-Kortic as a way to make puzzles that aren't available on the normal spherical puzzles. So the idea here is you take these geodesic systolic loops that they can't be shrunk to a point, and you do the twists along those. And we talked about that, and I actually did make a working puzzle back then, but I wasn't super happy with it. And the reason I wasn't is because it required the stickers to come off the surface during a twist. Anyway, when I was preparing for this talk, I had the insight of what it would take to make it work so where that didn't have to happen. So this is a puzzle showing some twists. They end up, the way I'm showing them right here is so that you can see the hyperbolic pants. You can see it's an order 4 thing. It takes 4 to go, kind of like a Rubik's Cube to go all the way around. And then there you can see the hyperbolic pair of pants, and then it solves the twist. And then I'll switch to a slide showing it twisted up. If you start doing it in a way that they actually interact with, the twists actually interact with each other, then you have a puzzle to solve. And of course, the puzzle guys solved this within a day or so. And I'm not sure if Andrew's here or not, but he had this great quote when he was writing about it. Since all the twists use geodesic motion, it really forces you to figure out how to use holonomy to get the pieces in the right orientations. And we're having more fun developing this. They've given me some really good ideas about how to make the twist controls better, so that's going to be a project that's going to be coming after this. All right, TilingBot. And Gabriel, by the way, TilingBot is no more. I retired it with the Elon Musk fiasco takeover a couple years ago. I have had requests to move it over to some of the new social media platforms, and it is on my wish list. I don't know if it will happen. If anybody's interested in helping with that, I would be happy to participate. But this is in prep for coming up for trying to make pictures of 350 cell. I was just going to show that on this cover of the Klein Quartic. So the 7.3 tiling is a cover. We can unroll the Klein Quartic and repeat it infinitely many times on this. You can start looking at things like this. Like this is an example of layers. And this is really interesting about the 7.3 tiling. This was a TilingBot post. If you count the number of objects and layers as you move out, they're 7 times the Fibonacci numbers, and which is neat and interesting. And why does that happen? This is from the puzzle program I was just showing you. And the difference here is this is showing that first layer, but with the identifications turned on. And so you can see a lot more cells up around, or a lot more tiles up around the corners, which are just copies of these being repeated. So some of the pictures coming up, I kind of wanted to show the difference in showing layers in those two different styles, because we're going to use it to understand the higher dimensional case. This isn't a completely abstract talk. I have a few slides with physical things because I've enjoyed shapeways, done quite a bit on honeycombs with Henry, and my wife laughed at the title of this slide when I was showing her. She's like, "That's obvious," but the reason I said that was because I remember the first time that Henry and I worked on a hyperbolic model, and it came, and we were sharing and talking about it. He's like, "They're so cool to hold in your hands," and there really is something that you see when you're holding and turning something over. You see different things. So this is the 14 Gon. This is a model I made, the 14 Gon, that shows the 336 symmetries of the Klein Quartic, and you can see the 7.3 tiling in there, and the dual 3.7 tiling too as well. I also thought I would share this one because I tend to go down these crazy things. And this is the Bulatov van model. Vladimir, I'm sure he's often here, so I bet he's here. But I use this, I got into surfing for a while, and I use this to make a custom surfboard. And this has some neat connections with some images I'm coming up, that are coming up too as well. So there's a couple physical things, and this is what is neat to connect it to. So in prep to go up a dimension, we'll start putting this Klein Quartic into the higher dimensional hyperbolic 3 space. And so this is a picture that makes it look a lot more like the dodecahedron. And this whole Matt had the whole sign petition for not having hexagons on the soccer balls. And I always thought that was okay, maybe even better in some ways, because in hyperbolic space, you can actually make polyhedrons with objects that have larger number of sides per face. So this is made of all of heptagons, and you can, like, if you look for the white one, for instance, you'll see it repeat. You'll see it repeat a little bit after a while. You'll see it repeats after 3. You'll see all 3 of the. So there's one, and then of the 2 opposites, you'll see another one. There's the next one right there. And then you'll see the third one, and then it'll come back to the white. So we're looking at this in hyperbolic 3 space, and we can think about starting to stack these together now. To get dodecahedron to get to 120 cell. So we're going to stack them together. We're going to stack together these abstract objects in hyperbolic 3 space and glue them up. Anyway, so I want to show the next one because this is the same thing, but this is with the dihedral angle that I'm going to use. So this has the same dihedral angle as dodecahedra have in the 120 cell, 120 degrees dihedral angle. And I've got a question for y'all. And if you can't think about your answer, I think it's a fun thing. I will tell you that I used one of the ball models to draw this, either the Klein or the Poincaré. So if you're familiar with the Klein model and the Poincaré disk model, in 2 dimensions, they're similar up a dimension. And the question for you is, which one did I use? And I've got the answer on the next slide. So I learned this from Wendy Krieger in the Google Plus days, and I heard she actually taught this answer to Conway even. So it's not necessarily fully intuitive, but have your guess ready, because I'm going to show you this same picture from the side. Okay, so that's the answer. It's in the ball model. So these are all the faces are portions of spheres, and all the edges are portions of arcs orthogonal to the boundary. And you can also see the ball at the top here. It has very little curvature. I'm very zoomed in, which is an interesting thing about the last picture that wasn't obvious, is how small, how far away towards I had to push things to get things to fit, to get the right field of view. And another interesting thing I want to point out here is how many tiles I had to draw here. So even though, let me go back, even though this, at some points, one heptagon will block everything behind it, there's something like 2,500 tiles here, and I draw these with the fundamental tetrahedra, and there's something like 35,000 there, and that was required to be able to get enough so that hyperbolic space is so weird, it just gets so big so fast. So the way that I word this is that azimuthal models, which means all the angles are correct from the origin, are anamorphic. So you can't tell a difference between the Klein and the Poincaré. It could have been either. I used the Poincaré, but it could have been either. The lighting is not realistic. It's because I'm using a shader here called Pauvre. But you wouldn't be able to tell otherwise. So it was a little bit of a trick question. Anyway, hopefully some of you got an enjoyable insight from that. Okay, so let's jump up a dimension. It turns out if we take 350 Klein quartics and start stacking them together, that they fold back up into themselves, a lot like the 120 cell, into one of these abstract regular polytopes. And I had fun for a couple years thinking about this object, and I thought it was new, and I found out later that it was the first paper I know about it now was in 1990. So it's been around for a long time. This is the group presentation, the third line there, which is really the mirrors. So just like the 120 cell, there's a fundamental tetrahedron that has 4 mirrors, and the whole thing is generated by reflecting across the four faces of that. And instead of having the difference, this is very much like the presentation for the 120 cell, except there's a 7 here instead of a 5. And there's also this extra thing here, which I didn't talk about much, but those systolic twists on the Klein quartic actually end up going across 8 edges before they repeat, and that's related to what's going on here. I used gap a lot to investigate this, so it's a bit of what illustration looks for me. I went ahead and took a screenshot of the gap coset table, and then the numbers in here correspond to cell numbers, and then I coded things around this, and I became quite familiar with a number of the things in here as well. So it's kind of interesting just to observe as you're trying to get your head around certain things, kind of what your brain ends up digesting. Here's just a comparison between the 120 cell and the 350 cell. The dual to the 120 cell is the 600 cell. The dual to the 350 cell has 4,900 vertices. So these numbers admittedly get quite a bit unwieldy. Here, there's the orientation preserving group sizes I've listed there too as well. And it's a picture of the 120 cell in the background from a program that I wrote prepping for the Magic Tile program, which is also, there'll be links to that too as well. Okay, so we're gonna take the analogy from this paper from John Sullivan, who I got to meet at one of the illustrating math things, which was really cool for me. He wrote a paper where he talks a lot about, or he had a section where he talks about all the symmetries of the cells in the 120 cell. So what we're going to do is we're going to take the symmetries he talks about in those paper and then look at it in the 350 cell and see if we can make analogies to it. And before we start that though, why doesn't it have 336 cells? Because my first thinking was because of the 120 cell, and I wasn't alone in this. I was talking to Scott, and he and a friend had the same guess too as well. It would be so cool if I was Math God, if the number of symmetries of the object were the same as the number of symmetries of the Klein cortex were the same as the number of cells in this higher dimensional object, like in the 120 cell. But this turns out to be really rare. The 120 cell is very special for that. The number of cosets is rarely, so the number of cells is rarely equal to the size of the subgroup. And the 120 cell is even more special on this front because um, if you interpret the symmetries of the dodecahedron as quaternions and four-dimensional space, it actually encodes the positions of the dodecahedron of the 120 cell, and that's even more special. And one of the most beautiful things I find in mathematics, actually. And I really wanted to find that here too, which I didn't. Spoiler alert! But I haven't given up hope yet. All right, I'm going to skip that last part. Okay, here's another, what does mathematical illustration actually look like for me? And 90% of the time, this is what it looks like. I'm in GAP or I'm in code, and it might be fair to call this research, but I do think this is an important part of illustration. And a lot of times the hurdles, the sort of practical hurdles I have to get over, like rendering time, for instance, are good for me because they will let my brain have time to think about whatever it's working over and trying, like in terms of trying to make these analogies, for instance. All right, I reached out to Saul and Henry about their paper, Puzzling the One Cell, and asked them if I could show this because the next pictures are going to be the analog of this for the 120 cell. So this is from their Puzzling the 120 cell paper, and you see a dodecahedron at the left there, and then you see at each face, we start adding layers and we go out. So at each face on the first layer, B, you see another orange dodecahedron surrounding it. At C, you see ones that are now living kind of over the edges of that original red one. And then D, or sorry, maybe the vertices. And then the D is the edges. And then, no, D is the faces again, sorry. And then E is the edges, and E is the hemisphere of the 120 cell. Also, one thing I wanted to point out about D is it's a little bit different than all these other layers here too as well, because it's the only one where the cells aren't connected. So I try to draw analogous pictures using my Pavre setup and honeycomb code. And so this is that central cell. And because of the identifications, all those little dots around it are copies. This is on the 350 cell, are copies of this central cell. So they're all the same cell. It's kind of like looking at that full tiling of the Klein quartic. Here's the next cell surrounding it. So we've got, for every face on that central cell, which is only 24, even though these pictures have a lot more in them, we have another cell surrounding it. And I'm using the same colors that Saul and Henry did to try to match it up a little bit. So there's 24 at this level. And one thing I wanted to point out here is, you can't see this in their picture, but you can see it here. I'm looking at the outside of the ball model. So this is kind of, in some ways, this is, abusing illustration, but this is what you might call the two skeleton of a honeycomb. So the two faces, the heptagons, are all shown as planes here. I'm not filling in the interior of the cells. Whether Henry and Saul did that, I suspect they didn't. You can't tell from their pictures, but here you can kind of see from the inside. And the reason you can see the inside is because these cells are something called ultra ideal, which means they're kind of so big that they don't close back up in themselves into finite volume. So that's layer 2. Here's layer 3, yellow, same colors, and these are fun to stare at. We can debate how how much intuition they give you, but doing the coding and everything to get these layers. In fact, coding how to even determine which ones to draw color was it was a good learning experience for me. So I'll keep going down the layers and keep showing them. The last 5 layers I just show all at once. And here it looks like there's not a lot going on in the bottom right because everything's getting so far away in hyperbolic space. I could have redrawn. I could have done moved things in the model in hyperbolic space to get it more centered, but I kept everything in the same view for this model. And the reason I did that is so I could put them all together. And this is that cover slide. So this is a picture of the 350 cell colored by layers shown in the Poincaré ball model. And I think it's a pretty thing, and I think there is stuff to look at here and insights to be gained. This is that exact same picture. Let me go back and say you can't see the red one here because it's blocked off by the view. You can't see that central cell. Here you can, because this is a picture just on the boundary at infinity. And so, and then stereographically projected to the plane. So this is the same picture as the last one, but this is more like pictures that Henry and I did in our paper on hyperbolic honeycombs. And so you can study this in a similar kind of way, maybe in a little bit more analytical way, or the previous one might be a little bit more on the artistic side. Okay, I'm not going to do a bunch here, but I'm just going to point out a few things. Here's the counts of layers on the 120 cell and the 350 cell comparison. And those first layers I was showing you from Saul and Henry's paper, there's different ways you could count layers. They're kind of layers by distance from the origin. If you look at the cell adjacency graph, there's actually less layers, and that's what these counts are. It's interesting that the 350 cell has less layers from that perspective than the 120 cell does. So it gets bigger faster and then wraps back onto itself faster. The ones I've highlighted in red here are like that one that I pointed out that aren't connected. And so layer 6 and 10 on the 350 cell are the same. You end up with these disconnected cells that aren't touching each other. And okay, just looking at my notes, making sure I'm not forgetting anything. The meaning of life is in here too as well. You see, there's a 42 there. The Klein quartic has 84 edges, but that is a difference between the 120 cell and the 350 cell. Is that the layers on the 350 cell that are above edges actually, for whatever reason, they get divided in half, and I want to understand that better. I just thought I'd sneak this one in. This was John Baez put this on his Visual Insight post, but it's related to this too because it's that same honeycomb. It's called the 733 honeycomb, and what that means is it's heptagons, 3 surrounding each vertex, and then those cells 3 surrounding each edge. And if you graph make all the colors the same on the full honeycomb, and graph the plane at infinity, you get something that's homeomorphic to the Sierpinski carpet. And so to me, that's another just kind of mind-blowing quick fact that's interesting to share. I think when illustrations move, this is the same honeycomb again, just another view, that it's huge, and for understanding too as well, and it can make a really big difference. This is just a Euclidean motion, not a hyperbolic motion, because it's a lot easier to generate that with my personal rendering process. But it's another way of illustration acting. Okay, so now I want to talk about trying to make analogies out of the rings of the 120 cell. So the 120 cell is divided into these rings that are 10 dodecahedra long, and they cycle together through fibers of the Hopf vibration. And so this is just turning some of them on and off and showing some rotations around. So here's 2 adjacent rings with a rotation into the 4th dimension, which causes some fun warping of some of the dodecahedra, even though they're all the same in space. So in 4-dimensional space. So the question is, what's the analogy for the 350 cell? So here's a similar picture, and this took me a lot longer to draw because it's a non-Euclidean transformation. And so going back to the 2 opposites yet again, so we have that central cell, and then we pick one adjacent one, and then we find the 2 opposites, and we keep adding and going past. So at each level, we're adding 2 more instead of 1, and they fold back in on each other. And this is a picture of that. And there's some interesting stuff here too that I'm excited to share with y'all. This is what mathematical illustration looks like for me. This is me trying to figure out the shape of those rings. So over here on the right here, you can see this node at the bottom is one of the cells, node cells, and each one's connected to two others because there's three opposing faces. And they end up connecting back to each other. There's 14 of them that connect together instead of 10, and they connect together with a more complicated topology. It turns out that this is called the Heawood graph, and there's some cool things about that too as well. One thing that I had really hoped, because the 120 cell is connected to the hot fibration, there is an analog of hyperbolic hot fibrations, which has been part of past adventures. And I had hoped that they would match up in a similar kind of way. I haven't lost hope on this too as well yet, but it doesn't seem to. And the reason is that if you divide 350 by 14, you get an odd number, or at least part of the reason is, part of my understanding is. I have been able to make, if I take half a ring, I have been able to make those fit together and fill out the whole space in my code, and wonder if that could be related to the hot fibration. So in this beauty contest, I've talked about how the 120 cell, the rings partition them and they follow the hot fibration, and it's so beautiful. Well, in the 350 cell, they don't partition the whole space, unfortunately. Half a ring does. There's like a doubling thing there. But the ring that gets made is a Heawood graph, and that actually has the same symmetry group as the Klein quartics themselves. It has PSL27 symmetry group. So we get this kind of meta PSL27 of PSL27s, and I think that's very beautiful and wins the beauty contest. So +1 for Math God on that particular thing. All right, I'm gonna have to speed up a little bit. If you take the rings, because of the hot fibration, if you take the dodecahedron faces, each one of the 12 faces corresponds to one of the rings. And this was some fun yin-yang pictures based on that. So I'm showing the dodecahedron here too as well. And you can see I'm coloring the rings in such a way that it makes a yin-yang on the base space. And the reason I even brought this here too is because I was able to make the analogy work here on the 350 cell in a pretty neat way. So the two white circles there are rings. So if I start off with one of the rings and I get all of the adjacent cells to it, and I'm doing all this in code, like how do you, Henry asked me once, how do you know this? I have a bunch of functions that will let me like calculate a ring, calculate a shell, see if they're connected, and whatnot. So start off with one of those white, it represents a ring, one of these white rings. I get all the cells around it. That's the black area. And there's 147 of those. It turns out those enclose another ring on the same not hemisphere, but the same hemi section of the 350 cell. If you get all the adjacent ones to that, you end up repeating on the other side. So there's 175 cells that make up half this thing, and they're divided in this way. And they're connected back to this concept of a ring too as well. And I wanted to call out Edward Gorchaika here. He actually supported me on Twitter with, we did a project that was similar to this, which was the inspiration for this. And he passed away a few years ago, and but he is still here with us. I thought I would share on the what does mathematical illustration actually look like when I was trying to adapt what he and I did to this yin yang thing for this talk. It got messy and I got lost, and it looked like this at one point. So anyway, behind the curtain. All right. Looks like I've got, how am I doing on time, Aaron? I have 2 minutes left on my list, but anyway, I wonder if I should speed up some.
Yeah, we started just a couple of minutes late, so I think you've got about 5 minutes.
Okay. So this is the 120 cell, can be divided into two tori. This is back into John Sullivan's paper. And what I've done here, instead of, I've put a slice at the hemisphere of the three sphere, and I'm just moving it along one of those tori. And it's that two skeleton again. So what you're seeing here, the gray, is where that two skeleton's getting sheared, and the white and the black are the interior of the dodecahedra and the cells. And so it's an interesting way of dividing. It's different than, you can also divide the 120 cell into two halves, sort of hemispheres, but they also has this beautiful torus decomposition, and that's what this is. And this is a way of looking at it. And this is a similar thing on the 350 cell. So what I did here was I put a slicing circle inside the hyperbolic model with all the two hemi sections colored black and white. And I started moving from one to another. It's different than the 120 cell in a couple of ways, but it's a very similar kind of thing. And you can, it's pretty to watch. Again, I think these things do get so abstract that it's legitimate to say maybe this is past the point of actually increasing understanding, but it's an analogous picture to the last one in some ways. Oops. And this is increasing the cut size, that same as the last and not animated, but increasing the cut size to be the plane at infinity. And you can see there's so much structure in here. There's really 350 cells after identifications, but there's a lot of structure in here, and I think a beautiful picture. So one of the other, I'm actually not even going to go into this because I don't even need to, but this is one of the other, the 120 cell can be composed into these buds, which line up with the hypercube. And I'm just going to jump to where I felt at this point on the 350 cell. It made me think of this scene in the Matrix. If y'all have seen it, but change the spoon to math. So do not try to bend the math. That is impossible. Instead, only try to realize the truth. There is no math. Then you'll see it's not the math that bends. It's only yourself. And I had that experience on this. I've had that experience on this project so many times where I'm like, ooh, it should, the symmetry group should be PSL 225. But then you think about it and you look at it a different way, and it fits in a different way. So I bend myself to make the analogies come out instead of trying to make the math do what I want to do. And I'm a Platonist at heart, so I actually do believe there's math out there, but I still thought this was a fun analogy. So we'll watch him get an insight here, and then I'll jump to the next slide. There you go. He just figured out something about the 350 cell. Here's some physical models. I've actually got these here in front of me too. One from Shapeways and one laser crystal, which I think are beautiful. Both of the full honeycomb. And I'm going to skip this. This is connection to some physics stuff, but I don't think we have enough time for it. And there is always more to do here. I have had lots of ideas preparing for this talk. I'm probably going to take a rest, but I have more things to go look at. And they're here. And one of the biggest of those, like if you were math god, what would you do in the parabolic case? So here we can ask the same question for hexagons instead of heptagons, 5 to 6 to 7. And it turns out these abstract regular polytopes do exist, and the links to the papers are in these two as well. Okay, so get to the summary. It really does often feel like I don't understand these at all. I have the joke here, para-understanding. Sometimes I'll gain an insight and I'm like, oh, wow, that's so cool. And it'll disappear and it'll come back. But illustration has been huge in this project. The act of illustrating myself, making illustrations act themselves, and then preparing to share the illustrations with this community. And I realized during this that a 350 cell puzzle is inevitable. It's going to happen, and people are going to solve it. Like, there's just no question about it. And if you didn't believe me, Nan has already made an 11-cell puzzle, which has been solved. Another one of our members made a puzzle based on the 633 hyperbolic tiling. So it's totally possible. And then I have a new slide, which is less than a week old, because some folks in the hypercube group already are writing something that is just about there. And they sent me this picture. We had to meet together, and it was so much fun talking with them. The reason that they have more, you see more lines here instead of just the normal Sierpinski looking picture, is that you need to illustrate where your pieces are. and they need that for a frame of reference to know where to click. But I sent them the presentation of the 350 cell, and they put it into their program, and they brought this up, and they made this picture. And this is only a week old, and that's another cool thing that's come out of doing this talk. All these links are on are going to be on the link that I send you, which I will just jump to here. If you go to roice3.org, Illustrating Math, it's got just a link to these slides, and then the slides themselves have all these links in it. This is another one of my cats, Collie, and this, when I gave a talk at the 2019 Illustrating Math thing, this wouldn't play correctly, so I put it back in here because she gets a moment of understanding here looking at some honeycombs. You can see her take a step back. Ooh, yeah. Anyway, thank you very much. I think hopefully timing is good.
Absolutely gorgeous. Thanks so much, Roice. There's some posting happening in the Discord. I
Cool.
feel like we could potentially take one question before shutting down the Zoom. What do you think, Aaron?
I'm sure we could do a quick question.
And I'll go hang out on Discord after this too. I can only do one thing at a time, so I'm not on there yet, but I will go.
Yeah. Anybody's dying to hop in. If not, we could hop over to the Discord as well.
I'm certainly willing to ask a question, which I wanted to ask about the hop lines in hyperbolic space, because that's that sounds. Could you show that picture again and say what you were suggesting? Say what you're saying.
Yeah, and Saul, to remind you, we had you and I with John and a graduate student had a fun in the old Google Plus days. We had a fun conversation about this, which I think I linked to in the links here. The hop vibrations in hyperbolic space, turns out there's multiple kinds, and in some ways they aren't as nice as the 120 cell. They aren't. You can't, except for this one at the bottom right, you can't move any fiber to any other fiber in without breaking the geometry. So I think the word was fiber-wise homogeneous or something like that. Anyway, yeah, cool.
Thank you very much.
Yeah. All right, I'll see you all in Discord.
Okay, well, thank you, Roice, and thanks to our show and ask speakers as well. Thanks to everyone for coming. Gabriel, do you want to echo those your list of links again? That would be great. I'm not going to run through what they all are. I think everybody probably knows at this point, but just to remind you, or if you missed it at the very beginning,
Yeah.
there's a list of links for various things. The only one I will echo is the show and ask sign up. If you would like to give a show and ask presentation, please follow the first link and do that. And then all those other links we've already talked about. So I think I will stop the recording and people can continue on the Discord, and we will resume again next month. Thanks, everybody.